Hello, viewers, and welcome to yet another exciting episode of Mathematics brought to you courtesy of Unlockwise. I am your host, Martin Tatenda Chipiro, known in the social circles as Maths Guardiola. And today we'll be doing a revision of almost the whole syllabus because we are preparing for Maths Paper 1 for those who are writing their O levels in few days to come. Right. So behind me here is the syllabus in miniature. Right. We have 14 topics which we do in mathematics. Right. We have real numbers which can be broken down into a lot of subtopics and concepts because people mistake topics with subtopics and concepts. I often hear people say we have 40 topics in mathematics. No, we only have these 14. And we will actually break down some of the topics so that we cover as much content as we can that will be examined, right? For example, let's say under real numbers, we have number types. We have number types. Here, that's where you get to learn about odd numbers, even numbers, prime numbers, factors, multiples, highest common factor, lowest common multiple, and even rational and irrational numbers, right? That will be the number concept subtopic, but all other types of numbers I was mentioning, they fall under number types, which is a concept, not a topic, right? So from there, we have standard form, right? Standard form, what I want you to know under standard form is to express a number, you need to know to express a number in standard form, of which to express a number in standard form is writing a number in the form a times 10 to the power n, of which a, this one, your a should be a number between 1 and 10. A is a number between 1 and 10, right? And your n here, n is an integer. Now, what is an integer? An integer is a number which is either positive or negative. And I often like to include zero, right? Because we can even have the power as zero, right? So I just want to show you how we can write numbers as in standard form. Right. Let's say we have a number which is 0,003. 0,003, we want to write it in standard form, of which I said it's writing a number in the form a times 10 to the power n, right? Where a is a number between 1 and 10, and n is an integer. So we will refer to these numbers as small numbers. Numbers less than 1, we will call them small numbers. And the power of 10 is negative. So what I want you to know is when you have a number like this, you count from left. When you see a non-zero number, then just after that, that's where your comma should be. So let's say we have 0,03 and we want to put this number in standard form. You move your comma from left to right. After the non-zero number, that's where your comma should be. So our first non-zero number is 3. So our comma should be here. So we are going to write this as 3, 0 times 10 to the power. How many times does our comma move to be on the position it now has to be? 1, 2, 3. But remember, I said the power of 10 is negative. So we are going to have this as negative 3, right? Let me give you another example so that you understand this better. Let's say we have 0,0256 and we want to write this in standard form, right? So what we are going to do is we are going to check from left to right. After our first non-zero number, that's where our comma should be. So from here we have 0,0256 and our first non-zero number is 2. So after 2, that's where our comma should be. So we will write this as 2,56 times 10 to the power minus, how many times does our comma have to move to go to this position? 1, 2. So we will have it as 2,56 times 10 to the power 2. Okay, fine. So this is how we write what we call small numbers in standard form. Let's move on to what are known as large numbers. Now, what I will refer to as large numbers in this lesson are numbers greater than 10. Let me call this large number. These are numbers which are greater than 10. Now, for numbers which are greater than 10, the power of 10 is positive. Okay, the power of 10 is positive. Right. So, for example, let's say I have 1250 and we want to express this in standard form. So, initially, our comma is supposed to be here after the unit digit, right? Because these are tens, these are hundreds, these are thousands. Okay. So, our comma initially is here. And now we'll still be looking at numbers from left to right, and after a non-zero number, that's where our comma should be. So if you are to check, our first non-zero number is 1. So our comma is supposed to be here. Let me put a different color. This is here where our comma should be. So if we are to rewrite this, we are going to have something like 1, 2, 5. Some might actually want to put the 0, but writing it or not writing it won't change anything. So how many times does our comma move from here to the place where it is now supposed to be? 1, 2, 3. So we have this as 1,25 to the power 3. Okay. I will give you another example. Let's say we have 23,430 and we want to express this in standard form. We will still do the same thing. Initially, our comma was supposed to be here. And now, looking from left to right, our first non-zero number is 2. So our comma is now supposed to be here. So we are going to write this as 2, comma 3, 4, 3 times 10 to the power. How many times does our comma move? 1, 2, 3, 4. So this is going to be 2, comma 3, 4, 3 times 10 to the power 4. Now, just to check your understanding, I will give you something like this. Let's say we have 12, comma 8 times 10 to the power 3. At first glance, this might actually look like it is in standard form, but it is not. Why? Because from my definition, I see that the number here should be between 1 and 10. But if you are to check this one, it's not between 1 and 10. We have it as 12, comma 8. So what do? We will first express this in standard form, and we'll have this as from left to right. Our first non-zero number is 1, so our comma is supposed to be here. So we have it as 1,28 times 10 to the power. How many times does our comma move? 1. And we still have this now, which is 10 to the power 3. And we can write it here as 10 to the power 3, right? And according to laws of indices, when we have bases, the same base, and we are multiplying, we will add the powers, which now means that we are going to have 1 plus 3, which will give us 1,28 times 10 to the power 4. So this is how we express numbers in standard form, right? So I want us to move from expressing numbers in standard form to changing numbers from standard form to ordinary form, right? So we are going to change numbers from standard form to ordinary form, converting from standard form to ordinary form. Now, let's say we have our number as 9 times 10 to the power negative 4, right? Since we have a negative power, it means that this one is a small number. So when we want to change it from standard form to ordinary form, we will come and write our 9 here, and this means that we have our comma here. And we are going to move 4 times to the negative side. So 1, 2, 3, 4. Now, this means that our comma is supposed to be here. And we'll write the zeros 1, 2, 3. And because we don't have any number here, we'll put a 0, which now means that this is equals to 0, 0, 0, 0, 9. Okay, this is how we express small numbers from standard form to ordinary form. Let me just give you another example. 8,35 times 10 to the power negative 2. So from this, it means that we are going to have 8,35, and our comma, because this is a negative, it's a small number, so our comma is going to move to the left. How many times? 2. So 1, 2. Here is where our comma should be. So we will have 0 here, and because we don't have a number here, we'll put 0. So we have 0, comma 0, 8, 3, 5 as our answer, right? So from there now, we want to talk about addition and subtraction in standard form. We'll talk about addition and subtraction in standard form. So we have different methods of adding and subtracting in standard form. But I would actually encourage you to change your numbers from standard form to ordinary form. Then you add in ordinary form. After you have got your answer in ordinary form, you change it back to standard form, right? That's a safer way of doing things. Although we can even use factorization, but not everybody is flexible with factorization. That is even why I encourage you to change from standard form to ordinary form and back. Okay. Let's say, for example, we have 6,2 times 10 to the power 3 plus 4,8 times 10 to the power 2. And we want to add these numbers and give our answer in standard form. So what we are going to do is we can change this one to ordinary form. How? I have just highlighted that. So we have 6,2. Because this one is positive, we will have to change to move how many times? 3 to the right. 1, 2, 3. So we'll put a 0 here, put a 0 here. So this becomes 6,200. And we are going to add it to, this is 4,8. And because we have 2, a positive 1, our as our power, we are going to move 2 positions to the right. 1, 2. And we'll put our 0 here. So it now means that we are going to have 6,200 plus 480. Now, if you add this two, we are going to have 6,200 and 480. This will give us 0,866. So we have 6,680 as our answer, and we convert this back to standard form. So this will give you from left to right. After the first non-zero number, you will get 6,68 times 10 to the power. How many times does our comma move? 1, 2, 3. So this is equals to 6,68 times 10 to the power 3, right? We can also have subtraction of numbers in standard form. Let's say we have 8,3 times 10 to the power 4 minus 6,2 times 10 to the power 3, right? Now, we change this number to ordinary form, and we also change this number to ordinary form and subtract, right? Like this. We have 8, comma 3 times 10 to the power 4, which means we are going to have 1, 2, 3, 4. And we also change this one, ordinary form, which will give us 1, 2, 3. Right? So basically we have 83,000 minus 6,200. And this will give us 0 here, 0 here, 8. Here we get 6, 7. So we are going to have 6, 7, 6, 8, 0, 0. And if we are to convert this to standard form, we have 7,68 times 10 to the power how many times? 1, 2, 3, 4. So this will be 7,68 times 10 to the power 4. Okay, so we can also have multiplication and division in standard form, right? We can have multiplication and division in standard form. Now, so under multiplication, numbers will multiply each other and powers of 10 will multiply each other, right? So I will start with the basics and then I will explain what your examiners will play around, right? So the basics is, let's say we have 3 times 10 to the power 2 being multiplied, let me put this in brackets, being multiplied by 2 times 10 to the power 3. So numbers are going to multiply each other and powers of 10 are going to multiply each other, right? So we are going to have 3 times 2, which is 6. Then we have 10 to the power 2 being multiplied by 10 to the power 3. So when the bases are the same and we are multiplying, we add the powers, right? So we are going to have 6 times 10 to the power 5. Simple, right? But now, what your examiners do now is they will give you numbers here, which after you multiply, they will give you a product which is greater than 1 and also greater than 10. And I mentioned that for a number to be in standard form, it should be in the form a times 10 to the power n, where a is a number between 1 and 10. So what do? You have to put it in standard form after multiplying. Okay, how? Let's have something we can relate to. Let's say we have 4 times 10 to the power 5, and this is being multiplied by 5 times 10 to the power 2, like this. So if numbers multiply each other and powers of 10 multiply each other, we are going to get 20 here. Then we are going to get 5 plus 2 here. And this will give us 20 times 10 to the power 7. But this 20 right here is greater than 1 and greater than 10. So what do? You have to put 20 in standard form. This will be 2, 0 times 10 to the power. How many times does the comma move from here to here? Is 1. And then we are going to multiply it by 10 to the power 7. And we have 2 times 10 to the power 1 plus 7, which will give us 2 times 10 to the power 8. Let's hope you are getting the sense, right? You are understanding what I'm saying, right? Then we can also do division in standard form, right? We can have division in standard form. We can have division in standard form. So maybe before you start, I will start simple and then get a little bit wide, right? Let's say we have 8 times 10 to the power 4. And this is being divided by 4 times 10 to the power 2. Basically, numbers are going to divide each other and powers of 10 are going to divide each other, right? And 8 divided by 4, we are going to get 2. Then, if we are dividing numbers with the same base, but they are indices, right? They have the same base. Then, if we are dividing, we subtract, right? So we are going to have 4 minus 2, which will actually give us this is 2 times 10 to the power 2. Okay, right. So what will happen now is, let's say, as we are dividing, we come across a number like 3,2 times 10 to the power negative 3, and is being divided by 4 times 10 to the power negative 2, right? So what happens is our numbers are going to divide each other and our powers of 10 are going to divide each other as well. So 4 into 3, 2, 4 into 3 is 0, into 32 is, I think, is 8. We are going to have 0, 8 times 10 to the power, here is minus 3. And if we are dividing, we subtract. So it's 10 to the power minus 3 minus 2, right? So this is going to give us 0, 8 times 10 to the power minus 3 plus 2, because we have minus and minus, which will give us plus. So here we have 0.8 times 10 to the power minus 3 plus 2 will get minus 1. But our 0.8 here, is less than 1 and less than 10. So what are we going to do? We are going to express this in standard form, and this will give us 8.0 times 10 to the power, because we moved to 1. It's a small number, by the way, so we have the power of 10 being negative 1, and we also have this times 10 to the power 1 here, times 10 to the power negative 1, rather, this one. So it now means that we are going to have 8.0 times 10 to the power negative 1 plus negative 1. And this will give us 8 times 10 to the power positive, and negative will give us negative. So it's negative 1 minus 1, which will give us negative 2. Right? So this is how we divide numbers in standard form. So moving on to the next concept, right? The subtopic now is number basis. That is even why I was telling you that people think that we have a lot of topics in mathematics. No, we just have 40. But we have a lot of subtopics and concepts. We are still in the first topic, real numbers. But we talked about one of the subtopics, which is standard form, and those were some of the concepts now under standard form. So now we are going to look at what is known as number basis. Now, under number basis, we also have other concepts under the subtopic number basis, right? And normally we deal in base 10, which is known as the denary base, which is base 10. Of which in base 10, we have our units, our tens, our hundreds, our thousands, our tens of thousands, and so on and so on, right? So this is 10 to the power 0, this is 10 to the power 1, this is 10 to the power 2, this is 10 to the power 3, this is 10 to the power 4, right? Maybe we have 1 as our unit, we have 10 here, we have 100 here, we have 1,000 here, we have 10,000 here. So maybe for a number like 3,423, this means that we are going to have 3 times 1,000 plus 4 times 100 plus 2 times 10 plus 3 times 1, right? And if we are to write this, we can have it as 3 times 10 to the power, how many zeros? 3 here. 4 times 10 to the power, how many zeros? 2. 2 times 10 to the power, 1. And have this as 3 times 10 to the power, 0. And we call this expanding a number is powers of its own base, right? This is expanding a number is powers of its own base, right? So maybe let's look at another example. Let's say we have 142. Now, 142 means that we have 1 times 100 plus 4 times 10 plus 2 times 1. Now, this is the same as 1 times 10 to the power 2 plus 4 times 10 to the power 1 plus 2 times 10 to the power 0. And you might recall this being done this way at schools: 0, 1, 2, and you say that 1 times 10 to the power 2 plus 4 times 10 to the power 1 plus 2 times 10 to the power 0 is still one and the same thing. And this is what I will be using as we go forward. I just wanted to highlight where it comes from, right? You should know what you are doing and why, right? So allow me to maybe change the base, because we have a lot of bases as we have a lot of numbers. You might even be shocked to know that you started doing number bases when you were at primary level. You started doing number bases at primary level. When you were doing time, you know how time is number basis. We have 7 days in a week, right? And if the number of days exceeds 7, you change the days. Okay, let me highlight this. 1 week equals 7 days. And if we get to maybe 9 days, we will have to remove the 7 days from this. And we will say we have 1 week and 2 days. They get to 15, you say we have 2 weeks, 1 day. We should not exceed 7. We don't even need to use 7 in this space, right? When we reach 7 days, we just go a week, right? That's the same with number basis, right? So we also have base 24, which we use for hours, base 60, which we use for minutes and seconds, right? And in some past exam papers, this is even examined. You are told to add or subtract time, the days, hours, minutes, seconds, weeks. It's all part of number basis. And if you are to check your syllabus correctly, you have to do this in Form 1, right? It's under number basis in Form 1. So I am going to take it a step further from the number basis in form of time, days, weeks, whatever. And I'm going to do from base 2. I'm going to deal with base 2 to base 10, right? These are the number bases I'm going to be playing around with. But whatever I'm going to say apply to any other base, right? Okay. So the first thing I want you to notice is we are going to have this. We are going to express numbers as powers of their base outside base 10, because what I did was I highlighted how to express numbers as powers of their base in base 10. I will use this one: 1, 2, 3, 4, which is in base 5. And we want to express this in powers of its own base. And by the way, why I love this one, I often use this to explain that in base 5, we don't have 5. We only have 5 numbers: 0, 1, 2, 3, 4. There is no 5 in base 5. Similarly to any other base, we have the same number of numbers as the base, but we don't have that base number in that base. Let me repeat this because this is very important. In any base, we have the same number of numbers as the base, but we do not have that base in that as part of those numbers, which means that in base 2, we have two numbers, 0 and 1. To those who do computers, you know this. We call this binary. We have two numbers, 0 and 1, on and off. Okay. In base 3, three numbers, 0, 1, 2. We don't have 3 in this. And this will even help you to answer the question whereby they ask you to give you the largest 4-digit number in base 8. Largest 4-digit number in base 8 will be 7, 7, 7, 7. We have 4 digits in base 8. And there will never be another number which is greater than this in base 8. Okay? So, okay, enough of that. Let me go back to what I was explaining. Okay, so I mentioned that we do the 0, 1, 2, 3, and we express this as 1 times 5 to the power 3 plus 2 times 5 to the power 2 plus 3 times 5 to the power 1 plus 4 times 5 to the power 0. So this is this number expressed as powers of its own base, right? 1, 2, 3, 4, base 5 expressed as powers of its own base, right? So from here, I want to explain how we convert from any other base to base 10, right? Right. So we have two methods here. We can expand a number as powers of its own base and simplify, or we can do repeated multiplication. So I will show you both methods and you will choose the one you want. So method 1, I will use the same number 1, 2, 3, 4, which is in base 5, and I will expand it as powers of its own base. 0, 1, 2, 3, and this will give us 1 times 5 to the power 3 plus 2 times 5 to the power 2 plus 3 times 5 to the power 1 plus 4 times 5 to the power 0. And this will give us 1 times, what is 5 to the power 3 is 125 plus 2 times what is 5 to the power 2 is 25 plus 3 times 5 to the power 1 is 5. 4 times 5 to the power 1 is, to the power 0 is 1. So this will give us 125 plus 50 plus 15 plus 4. And if we are to add this, we will get 4 plus 5, that's 9 plus 5. So we will get 4 here. Carry 1. Then 1 plus 5, you will get 6 plus 2, you will get 8 plus the 1 we carried, will get 9. And this is our answer, 194. You can even write the base here, which is base 10. You can write it as 10, or you can write it as words as 10, or you can simply write 194. If we don't see any base here, it means that we are in base 10, right? If you don't write your base, it means that you are in base 10. Okay, so there is also method 2, which I mentioned as repeated multiplication. We have 1, 2, 3, 4, which is in base 5. So what we do here is we will multiply by the base until the last number. So 1 times 5, you will get 5. You add the next number, you will get 7. Then 7 multiplied by 5, you get 35. You add the next number, you get 38, right? 5, 6, 7, 8, right? And you multiply by the base, you get 40 here, carry 4. 5 times 3, you get 15. 15 plus 4, you get 19. And you add the last number. The moment you add the last number, you stop there. So you get 194 as well, right? So this is method number 2. This is how we convert numbers from any base to base 10. Okay, so we want to convert numbers from base 10 to any other base, right? We want to convert numbers from base 10 to any other base, right? Convert from base 10 to any other base. Right. So what you would do is you do repeated division with the new base number until 0 is reached. Each time noting the remainder, and you read the remainder upwards, right? For example, let's say we want to change 72, which is in base 10, to a number in base 5, right? 72, which is in base 10, to a number in base 5. So what you are going to do is we are going to say 72, and you will divide by the new base number, which is 5. 5 into 72, we get 1 here, remainder 2. And 5 into 20, we get 4, remainder 2. So we write down the remainder each time. 5 into 14, you get 2, remainder 4. Then 5 into 2, you get 0, remainder 2. And you read this upwards. This will give you 2, 4, 2, which is in base 5. This is how we express numbers. We convert numbers from base 10 to base 5, or to any other base in particular, right? So let me just do one more example, and then we move on. We want to convert 13, which is in base 10, to base 2. So we are going to divide 13 by our new base number, which is 2. 2 into 13, we will get 6, remainder 1. 2 into 6, we will get 3, remainder 0. 2 into 3, we will get 1, remainder 1. And 2 into 1, we will get 0, remainder 1. So we read our remainders upwards, we get 1, 1, 0, 1, which is in base 2. So this is how we express our number, which is in base 10 to base 2. Okay, so we also move to another concept. This one is interesting now, because they will ask you 2 questions in 1 question. I know this might actually sound confusing, but I'm right. They will ask you 2 questions in 1 question. supposed to convert from one base to another. What do I mean? We want to convert a number, let's say 432, which is in base 5, to a number in base 2. So there is no direct way of converting a number from base 5 to base 2. So what you are going to do is you are going to convert this number in base 10 in base 5 to a number in base 10, and then convert from base 10 to base 2. Right? So for convenience sake, I will use repeated multiplication, but you are free to use any method you want. So I'll multiply this one by 5 and get 20 here. I will add 3, then have 23. I'll multiply 23 by 5. This is 15. And then 5 times 2 is 10 plus 1 is. Then I'll add 2. This will give me 170. Now, this is in base 10. And I want to change this base 10 number to base 2. So I will divide this number by 2. That's some way. 2 into 11, that's 5. Okay. 1 into 17, that's 8, remainder 1. 2 into 58, this is 2, and 9, remainder 0. 2 into 29, this is 1. This is 4, remainder 1. 2 into 14, 7, remainder 0. 2 into 7, this is 3, remainder 1. 2 into 3, 1, remainder 1. 2 into 1, 0, remainder 1. So I am going to have 1, 1, 1, 0, 1, 0, 1, which is in base, right? So this is what we have. So from here, we are going to have addition and subtraction of numbers in number bases. We have addition and subtraction in number bases, right? Addition and subtraction of numbers in number bases. So let's say we have 3, 4, 3, and which is in base 5, and is going to be added with 4, 4, which is in base 5, right? So we also have two methods here. You can convert this to base 10 and convert this to base 10, add in base 10, then change the answer back to base 5. But I'm going to teach you a very cool way. If you don't understand this one, then you have to do it the manual way. Let's say we have 3, 4, 3, which is in base 5 here. And we have 4, 4, which is in base 5 as well. And we are going to add this. 3 plus 4 will give you 7, which is now more than our base, right? And I was saying we don't have the base number in that base, right? Which means that we don't have 5 in base 5 and even 7, 6, 7, anything more than 5, we don't have it in base 5. So Once we add here and get a number which is greater than our base, some even like to do this. 7, which is the answer we got here, minus the base, you will get 2. So you write your 2 here and carry 1. I will have to refresh your mind a bit to base 10, which is the one we are used to, so that you will understand what I'm doing. Let's say we have 23 and 19, and we want to add this, right? 3 plus 9, we will get 12. But we don't write 12 here. What do? We will write 2 and we carry 1. Why? Because we say 12 minus the base, which is 10, we will get 2. The 2, we write it here. And then carry 1. Why? We have removed a 10th. We have removed our base. Yeah. Some, they even prefer to divide by the base. And it's the same thing. 12 divided by 10, what do we get? We get 1, remainder 2. The 2, that's the one they say they are going to bring here. And the 1 here is the one they are going to carry. So that's the thing. That's the concept, right? So with that in mind, and me expecting you to be people who are writing very soon, you should be able to know this. This is just a revision. And write it one, by the way. So 1 plus 4 plus 4, we get 9. And now it's going to be 9 minus our base, which is 5. We'll get 4 and we carry 1. 1 plus 3, you will get 4. And this is in base 5, right? So this is your answer. Let's just verify by doing conversion from base 5 to base 10 and add, and then come back to base 5. So I have 3, 4, 3, which is in base 5. So I will multiply this by 5 and get 15 here. I'll add 4 and get 19. 19 multiplied by 5. This will give me 5 carry 4. 95. As I add my 3, I will get 98. Okay, fine. And let's see, 44 actually is 44 in base 5. We call them by their digit value when they are in other bases. So this will give me 20 plus 4, which is now 24 in base 10. So this will give you 98 plus 24, and this is, so here carry 1, 10, 12. So it's okay. So we are now at a point whereby we have to do subtraction in number basis, right? So what happens here is we have 3, 4, 1, which is in base 5, minus 2, 3, which is in base 5. I say that if you don't understand the method we are going to use, you can convert the number to base 10 and then subtract in base 10, then convert it back to base 5 or any other base you have been given, right? So we have 341, which is in base 5. We expand it as in powers of its own base, change it to base 10. And I say that if we don't write the base, it means we are in base 10. And 2, 3, which is in base 5, we can expand it in base as powers of its own base and have it in base 10. We subtract. After subtracting, then we convert the answer back to base 5. Oh, you can simply do this, right? We want to subtract, but we have 341 minus 23, which is in base 5. All right, so 1 minus 3, we can't subtract like that, right? We have a larger number at the bottom. So allow me to take you back to base 10 so that you understand what I'm doing. Let's say we have 23 and we want to subtract 9, right? What will happen is we have a smaller number at the top and a larger number at the bottom, and this cannot subtract. So what do? We somehow add a 1 here and call this 13, and we will add a 1 here also, right? But what does this really mean? What it means is we are going to add the base here. 3 plus our base. Remember I said we are in base 10. So 3 plus our base, which is base 10. 3 plus 10 will give us 30. Now, once we give our base here, we'll also have another number here. Or some might actually do this. This is how my primary teacher taught me. We borrow a 10 from this side, which makes this one. And we'll add the 10 here to make this 10 plus 3, which is 18. So we'll have this as 13 minus 9, which will give us 4, and then 1 minus 0, which is 1. So to those who do this, still one and the same thing. 13 minus 9, you get 4, and then 2 minus 1, you get 1. So that's the same idea we implement here. We have 5 as our base. What are we going to do? We are going to add 5 to this one, and this will give us 6, right? And we'll also add a 1 to this one, and we'll get 3. So 6 minus 3 will get this 3, right? 4 minus 3 will get this 1, and 3 minus 0 will get this 3. Let's hope it's as clear as I'm trying to make it be, right? So this was one concept again, a subtopic and its concept under real numbers. So let's move on to another subtopic under real numbers, which is known as scale and simple math problems. Now, I love this word, right? It's just scale and some simple math problems, right? So what I want you to understand is there are basically 4 concepts you need to know. One, you will be asked to express the scale in the term 1 is to n. Now, what this means is for every 1 centimeter on the map, it is representing 10 centimeters on actual ground, right? 1 centimeter is representing 10 centimeters on actual ground, right? So you may be asked to express the scale in this format, right? Then you may also be asked the value or the size, the length on the ground given the length on a map, right? You may be asked the length on ground, the actual length given the length on a map. And you may even be asked the length on a map given the actual length on ground, right? And we also go as far as talking about areas, area of on the ground given an area on the map, and vice versa. Area on map given area on ground. So what I want you to understand is this. If the linear scale of a map is 1:n, it means that 1 centimeter on the map represents n centimeters on the actual piece of land. That's one. Then I also want you to understand that if the linear scale of 1:n, if the linear scale of map rather, the corresponding scale of the map is 1:n squared, right? So what is going to happen here is this is going to be our linear scale, our scale on the map. And this is going to be the scale of our area, right? We are going to square the scale factor so that we get the area factor, right? So for example, let's say we have a town, right, in a map of a town, 10 kilometers is represented by 5 centimeters. Now we want to express the scale in the ratio 1 is to n. That's our first question. And the follow-up question, what is the actual distance if it is represented by a line of length 2 centimeters on the map. And then find the area of a plot of land that is represented by 10 square centimeters. All right. So from our question, 5 centimeters is representing 10 kilometers. So this means that we have 5 centimeters here, which is representing 10 kilometers here. So 1 centimeter is representing how many kilometers? We divide this side by 5 and divide this side by 5. So we end up having 1 centimeter representing 2 kilometers. Right. So what I want you to understand here is we want to express these units in the same dimensions. What do I mean? We want to have 2 kilometers in centimeters as well, right? So you multiply the kilometer by 1000. So it means that we have our 2 being multiplied by 1000 to give us 2000 meters. And we want to change the 2000 meters to centimeters. So how many centimeters make a meter? It's 100. So we are going to multiply this 2000 by 100. So we will just add the number of zeros we have on 100. So this is 1, 2. So it means that we are going to have this is 1 is to 200,000. Right? That's us writing the number in terms of n. This is our 1 is to n, right? 1 is to 200,000. So this is our scale. This is our 1 is to n. You express your actual distance in centimeters, right? So that we have 1 centimeter, which is representing the value of your actual distance in centimeters. So we can even remove the centimeters as the unit here, right? Then the next question asks us to find the value, the actual distance, if it is represented by a line which is 2 centimeters on the map. So I want you to go back to maybe having this as 1 centimeter being represented by 2 kilometers, right? And this is the safest way of doing this. We are asked 2 centimeters. So what we do is we will multiply here by 2 and we will also multiply here by 2, which means that 2 centimeters is representing 4 kilometers, right? And sometimes you can even be asked the the length on a map given the actual distance, right? Maybe you can be asked to tell us what would be the distance on the map if 2 points are 50 kilometers away from each other. So you just take your 50, right? 1 centimeter is representing 2 kilometers. And if we are asked about 50 kilometers, we want to know the value on a map. So you multiply both sides by 50. So this will give you 50 kilometers divided by 2. You have this as 25 centimeters, right? So having done that, we can also move on to the area part. Now I want you to see something because we have already dealt with this. I will remove this part and this part so that we can have more space to work on. Okay. Already we know that 1 centimeter is representing 2 kilometers, right? And I highlighted that we can square this to get our area of vector. So 1 centimeter times 1 centimeter will get 1 square centimeter, and 2 kilometers times 2 kilometers will get 4 square kilometers. So what we will do here is we have been given that we want the area of the plot on the land that is represented by 10 square centimeters. We want something that is represented by 10 square centimeters. So what we do here is we have 1 square centimeter over 4 square kilometers. And this will give us the plot we are asked is in centimeters. So square centimeters like this. So we want the value of the area of the plot on actual ground. So if we cross multiply, this will give us x times 1, which is equals to 4 times 10, which will give us 40 square kilometers. And you can even be given the area on the ground and be asked to find the area on the map. Anyway, this was scale and simple map problems. We want to move to a next topic. You remember me mentioning that we have a lot of topics, right? Like 14, but we have concepts and sub-concepts and topics, subtopics and concepts. You get it? So we want to move on to another topic, the second one, which is sales, right? So under sales, what I'm going to teach you for revision's sake is what is known as union, intersection, and complement. Now, I will draw some Venn diagrams and explain what I'm saying here. Let's call this set A, let's call this set B. If we say we want union, it means we want everything that is in A and everything that is in B. We are uniting everything that is in A and in B. So this is something like A union B. We have united everything. We have combined everything. Right? Then for something like intersection, we want what is in A and that is also in B, right? For example, we have set A and set B. The union part is this one. What is in A and also in B. All right. Then for the complement part, we want what is not in the specified region, right? Let's say we have this as our set A. If we want, okay, maybe let me write this as A intersect B. Then we want A complement. We want what is outside of A, right? What is not in A, like this. Okay, so I'll give you an example. I'll give you an example. Let's say our universal set has 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And set A is a set of vectors of 100, and set B is a set of even numbers. Right. We want to find A union B, A intersect B, and maybe A complement. Okay, so if we are to draw a Venn diagram here, right? This is our Venn diagram, and we can have this is our set A, this is our set B, right? Factors of 100 in here, we have 1. 1 is a factor of every number. Then 2 can get into 100. 3 want 4. Yes, it's a factor of 100. 5 is a factor of 100. 6 is not 7. Is not 8. Is not 9. Is not. And we also have 10. Then we have even numbers. Even numbers are numbers like 2, 4, 6, 8, and 10. Okay, so we want numbers which are appearing here and here. We have 2 in here and 2 in here, so we will write our 2. We have 4 here and 4 here, we will write our 4. And we also have 10 here and 10 here, so we will write our 10. Then the others who fall into this for A, 1 and 5. Then for B, we have 6 and 8. Okay, so I want us to look at this. Do we have 1 in here? Yes, 1 we have. Do we have 2? Yes, we have. 3? No. So our 3 will be in here. So we have already used 3, which is okay. Do we have 4? Yes. Do we have 5? Yes. Do we have 6? Yes. Do we have 7? No. So our 7, we'll put it in here. Okay. Do we have already? We now have 7. Do we have 8? Yes. Do we have 9? No. So we have our 9 in here. Do we have 10? Yes. Okay. So if you are to check now, A union B, we said we combine what is in A and what is in B. So this will give us 1, 2, 4, 5, 10, 6, 8. Sorry, they had to mix each other. I tried to keep them in order, but you get the idea. Now, we want A intersect B. A intersect B is this region. So A intersect B will be 2, 4, and 10. Right. We want A complement. Everything that is not in A. So we have 3, we have 6, 7, 8, 9. Let's see. 3, actually. 3, 6, 7, 8, and 9. You can even be asked A union B complement. What is not in A union B? This will give us, so the region which is A union B is this one. We want everything that is not in this region. So this is 3, 7, and 9. Okay. So let's hope you understand union, you understand intersection, you understand complement, right? Okay. Let me move on to yet another concept on another topic because it's a revision. I'm not going to teach everything. I'm just going to pick points, pick points, pick points. One of the points I want to teach, because a lot of guys ask me, why do we have to learn logarithms? We can't apply them in life. We can apply them, but it's not where you want it to be applied that matters. So I'm going to talk about a topic which is financial mathematics. Under this topic, we have simple interest, higher purchase, compound interest, but my topic of interest, my subtopic of interest is foreign exchange. Forex. And I will use an example that is in syllabus A, the last question in syllabus A, paper 1, whereby it says, on a particular day, 1 USD is changed to ZIG 28, right? You'll be our rate here, $1 is to 28 ZIG, right? So if you have $25, $1 is to ZIG 28. If you have $1, you will be given 28 ZIG. How much will you receive if you have $25? So what you are going to do here is you are going to use your 25 multiplied by US dollar, right? And what you do to this side is what you also do to this side. So we have 25 multiplying the Z 28. So this side you have it as 25 US. Yeah, and I expect everybody in Zimbabwe to know how to convert from US dollars to ZiG, even to Eco Cash plus 20% and everything, and the charges. Financial mathematics is one of my favorite topics. So if you multiply 25 by 28, this should give you something like 700, I think. As long as you put a dollar on this, I want to take time to multiply. Let's see. 28 multiplied by 25. Put a 0 here. Then this will give you 16. 6 carry 1. 2 times 2. You get 4 plus 1, 5. Then this one times this one, you get 40. 0 carry 4. This one times this one, you get 10 plus 1. You get 14. So 0 plus 0 is 0. 6 plus 4 is 10. 0 carry 1. So 1 plus 5, 6 plus 1, 7. You get 700, like what I have already mentioned. Me and money. Okay, so this is foreign exchange, part of your mathematics under financial mathematics, right? So from there, we are going to move to one of my favorite topics, which is graphs. And under graphs, I will specifically talk about under graphs, we have what are known as functional graphs. A favorite in paper 2. And we also have what are known as travel graphs. So for the sake of this revision, I will just talk about travel graphs, but I will be in the comment section responding to any question that may be posed on functional graphs, because it's a very easy topic. It's a very easy subtopic rather, which you will have to answer for your paper 2. Right, so let's dive into travel graphs, and I will talk of velocity time graph. One of the most requested concept under graphs by our students. So what I want you to understand is they are going to ask you 4 concepts, right? You are going to be examined 1, 2, 3, or all the 4 concepts. So I will list them here. The first one is acceleration. You will be examined acceleration, of which the formula for acceleration, you see it in books like A is equals to V minus U over T. This is 1. Some may even say V2 minus V1 over T2 minus T1. And I even like this one more because it will bring us back to the concept of coordinate geometry, of gradient, of which there is a very good video on Unlockwise channel, which I did some few weeks back, which will explain everything you need to know on gradient. So make sure you refer to that one so that you can even understand some more concepts on calculating gradient, V2 minus V1 over T2 minus T1, of which this one, in that case, it will be referred to as Y2 minus Y1 over X2 minus X1, which is even one and the same thing, by the way. Okay, so from acceleration, we will also talk about distance, traveled, of which by distance traveled, we will be referring to area under the graph. By area under the graph, we normally use these shapes. One of them is triangle, of which the area of calculating a triangle is half base times height. We also use rectangle. The area of calculating rectangle is length times width or length times breadth, depending on where you learned your primary. Okay, and we also make use of trapezium. I love this one. Half A plus B times height, of which A plus B are the parallel sides of a trapezium, and H is the height, right? Then maybe a square, which is side by side. It's okay. So having calculated acceleration, distance traveled, we can also be examined uh, average speed. Now, from your knowledge of speed, speed is equals to distance traveled over time taken. Okay? Distance traveled over time taken. Right. And we can also be asked uh, velocity or time at a given point. So what I will do now is I will draw my velocity time graph and then make some questions as they will be done, like as they will be made by your examiners, and then I will help you to answer them and make sure that you understand what you need to know. Right. So, or maybe let me do this. I'm going to draw and have this as velocity in meters per second, and have this as time in seconds, right? And maybe draw something like this. Right. And have this as cell. Right. So what I want us to do is I will be putting some questions and answering them. Right. The first thing I want us to understand is A, calculate the acceleration during one, the first 8 seconds, and two, the last 4 seconds. Right. So what I want you to understand here is you need to take the coordinates, the points here. For example, here we have 0, 0. And here we start with the x coordinate, or the time in this case, which is 8, and the velocity, which is 20. Right. And our formula to calculate acceleration is equals to v2 minus v1 over t2 minus t1. Right. And I will take my coordinates 0, 0, 8, 20, and whichever I choose to be my v1, then the other one will be my t1. Whichever I choose to be my v2, the other one will be my t2. Right. So let me call this T1 and call this V1. Call this T2 and call this V2. Right? So V2 is equals to 20 minus V1 0 over T2 is 8 minus T1, which is 0. So this is going to give me 20 over 8. Right? And 20 over 8 is maybe, because I'm not supposed to use a calculator, 2 into 8, 4, and 2 into 20 is 10. 2 into 4 is 2, into 10 is 5. So this will give me 5 divided by 2, which is something like 2, 5. And the unit for acceleration is meters per square second. So this will be my acceleration, right? And now I will keep this because I want to show you something as we go. Our acceleration during the first 8 seconds is 2,5 meters per square second, right? I want you to remember this. Right. Then we also want to calculate the acceleration during the last 4 seconds. So the last 4 seconds is from 16 to 20. So I want you to say this. From here, we have our time being 16 and our velocity being 20, to a point which is here where our time is 20 and our velocity is 0. Right. What I want you to see here is I can take any of the points to be my T1 and V1 and the other one T2 and V2, right? So I will call this T2 V2 and call this T1 and V1. Okay, so what is my V2? My V2 is 0 minus my V1, which is 20, over my T2, which is also 20, minus my T1, which is 16. Okay. From here, let me remove this so that we won't have confusion. So V2 minus V1 over T2 minus T1, right? That's what I have here. And this will give me minus 20 over 4. And this will give me minus 5 meters per square second. Right. What I want you to understand here is if you are asked, is acceleration, like in this case, then you write it as minus 5 meters per square second. But if you are asked is deceleration or retardation, you remove the minus sign and you write it as 5 meters per square second. Let's hope you are understanding that part. Then, having done this, we will have to move on to the concept I mentioned, which is now to find uh, distance traveled. Now, I said that distance traveled is area under the graph. So we want the distance traveled during the 20 seconds. So find the distance traveled during the 20 seconds. So what I'm going to do here, I'm going to kill two birds with one stone. As I will be explaining this, you may actually take the formulas and use them to mensuration of shapes, calculating area of shapes, right? So maybe we'll even talk about the trapezium because this one is a trapezium itself, this one. And some might actually want to use the triangle, rectangle, and triangle, and I will use it to check if the answer is correct as well. Okay, so what I'm going to do here is area of a trapezium is equals to half A plus B times height, where A and B are the parallel sides. Right, so this part is 16 minus 8, which is actually 8, plus this part is 20, and the height is 20 as well. So allow me to maybe simplify what is in the bracket first. I will get 20 plus 8, which is 28, times 20. So I will cancel this one and get 10 here. Apply 1 times 28 times 10, I get 280, which is my meters. Okay. Then maybe to those who want to break this down and check if it is correct, this is a triangle, half base times height. And this one is a rectangle, length times width. And the other one is a triangle, half base times height as well. Okay, so what is the base here? The base is 8. So allow me to write it here. Half base is 8 times, what is the height? It's 20. So this will give me 1, 10, and this is 80. Okay, so this part is 80. Then length times width, we have our length as 20 and our width is 8. So 20 times 8, this will give us 160. So this part is 160. And then this one, half base times height. What is our base? This one, which is 4, times half of 4 times the height, which is 20. So if this one and this one cancel each other, we'll have 1 times 4 times 10, which is actually 40. Right. So if you combine this 80 plus 160 plus 40, let me do this way. 160 plus 40, you get 200. 200 plus 80, you get 280, just like this one. Okay. And then from there, we have actually managed to talk about distance traveled. Let me remove some of the mess here so that you might actually see. Right. So another aspect I want us to look at now is average speed, right? We want to calculate the average speed. Calculate the average speed of the ocean. Right. So from what I've already highlighted, I mentioned that speed is equals to distance over time. And we have just calculated the distance and got 280. And what is our total time? Our time is 20 seconds. So our speed is actually going to be, I'll cross out this one, and 14 meters per second. This is our average speed. So I also want us to look at now my favorite part, because a lot of students ask me this part because they fail to understand what is happening correctly. So please bear in mind that I'm going to use two methods. One of the methods is of coordinate geometry, and the other one we are going to use cumulative addition or cumulative subtraction. That is even why I had to keep this value, which is the acceleration during the first 8 seconds. And to those who still remember, the acceleration during the last seconds is minus 5 meters per second. I will also need to use this one so that you understand what is happening, right? So you may be asked the velocity when time is equals to 4. The time is now 4, and we want to find this part. What is the velocity when time is equals to 4? So now we want to find velocity when t is equals to 4. And maybe when t is equals to 19 as well, we just play around with this. Okay, so you first have to calculate the acceleration. So because we calculated the acceleration before, I will concentrate on explaining what is going to happen. From here, we have 0, 0, 0 on time, and 0 acceleration. No problem. For every second, we are going to add this acceleration. So from 0, we have 2.5. The next second, we add the acceleration, we get 5. Because 2.5 plus the acceleration, which is 2.5, we get 5. On the third second, we add 2.5. And we will have this as 7.5. The other second, we add 2.5 and we have 10. Which now means that here our x is equals to 10. Maybe for you to understand this better, let me continue so that you see where I end. Right? Let me use red here. The next second, 5, we add acceleration, 12.5. 6, we add our acceleration, 15. 7, we add our acceleration, 17.5. On the 8th second, 17.5 plus 2.5, you'll get 20, which is actually this point, right? So when you are asked in terms of acceleration, you add the acceleration, add the acceleration. When you are asked in terms of deceleration, yeah, maybe the 19th second, what you are going to do is subtract from here, subtract your deceleration from here, like this. We want to find the velocity when t is equals to 19. So what do? We say this point 16, we have 20 as our velocity. This is our velocity, this is our time. For each second, we are going to subtract our deceleration or our negative acceleration, whatever you want to call it. 17, we subtract 5, we'll get 15. 18, we subtract 5, we'll get 10. 19, we subtract 5, we'll get 5. So this point is 5 here. Then if we get to the 20th second, 5 minus 5, you get 0, which is this point. Let's hope you understand it. Then I was saying there is a method we can use, which is like coordinate geometry, right? Under coordinate geometry, we know that y2 minus y1 over x2 minus x1 is equals to m, which is our gradient. So we will take our points here, right? This one is 0, 0. And this one is 8, 20, right? So for one y1 and the other one y2, let me have this one is x1, y1, and this one x2, y2, right? So y2, 20 minus y1, which is 0, over x2, which is 8, minus x1, which is 0, is equals to my gradient, this is it, right? Which is 20 over 8 to give me 2, 5, right? Square meters per square second. Right. So now I want to calculate this part, this one. So what I will do is I will say y minus y1 over x minus x1 to give me the gradient. Right. Now I want to show you this. You can pick any point here. You can even take this one or this one. I will take this one with 0, 0. 0 minus what is and the other one is 4, and the y value is the one I don't know. So you can take this to be your x1, y1, x2, y2, and have it here like this. X minus, of which x is now my y2, minus y1 is 0 over my x2 is 4 minus the other part is 0 to give me 2,5. Right. So what will happen here is you have x minus 0, which is actually x, over 4 minus 0, which is 4, to give you 2,5. If you multiply both sides by 4, this one by 4, and this one by 4, this one and this one will cross each other out. So x is equals to 2,5 by 4. 2,5 by 4 is 10, which is actually this one. Right? And let me clear the site so that I can explain this clearly and you understand it. So what I'm saying here is y2 minus y1 over x2 minus x1 is equals to the gradient, right? Or our velocity over our time is equals to our acceleration. No problem. So this point is going to give us 16 and 20. And this point is actually 20 and 0. But we want this point now, which is 19 and a value we don't know. Let me call this y. But what is going to happen here is our gradient is the same on this line, which means that we are going to have minus 5 here, which is equals to, let me call one of this x1, x2, y1, y2, right? So this is going to be my x1, y, let me call this y2, x2, and this x1, y1, so that when I subtract, I will have this as positive, right? So y minus 0 over 19 minus 20, right? This will give me y over minus 1, which is equals to minus 5. And if we multiply both sides by minus 1, this one and this one will cancel each other. So we have y is equals to minus 5 times minus 5 will get positive 5, which is actually this one. So let's hope it's clear. Right. So moving on to another concept, which is now bearing. Before I talk about bearing, I want us to look at what are known as parallel lines. And I will summarize parallel lines into what I call fun. The angle, if this one and this one is parallel, and this one and this one is parallel, and this one is parallel, it means that this angle is equal to this angle. And this angle and this angle, they add up to 180. And this angle and this angle are equal. Right. These are corresponding angles, co-interior angles, or allied angles, and we also have alternate angles. We call this corresponding angles. These ones are allied or co-interior angles, and these ones are alternate angles, right? So for corresponding angles, they are equal. Then allied angles or co-interior angles, they add up to 180. And then for alternate angles, they are the same, right? They are equal, right? Let me just write this a bit so that you understand what we need to work with. So let's say these are our parallel lines, and we have a line that cuts across our parallel lines. It now means that this angle is equal to this angle. And maybe this angle is also equal to this angle. Uh, this one and this one, this one and this one. Also, this one and this one. I think you get the idea, you get the sense. Even if we do this, so we have it here, we have it here, and we can also have it here. This one and this one are equal. Right. Then for this one now, angle inside this part and this angle, they add up to 180. And even if we have something of this nature, these angles, they also add up to 180, right? And we also have what we call alternate angles, whereby okay, this angle is equals to this one, and maybe this angle is equals to this one. These are what others refer to as Z angles, and they say Z angles are equal. Now, having said this, I want us to talk about bearing, because bearing, uh, we will use these properties of parallel lines. So under bearing, I want you to remember these three things. These three things are very, very important. The first one is always measure the angle from north. So always measure the angle starting from north. And I also want you to understand that we also always measure the angle clockwise. And then you need to write the bearing as three figures. These are the three things you need to understand. We always measure the angle starting from north, always measure the angle clockwise, and write the bearing as three figures. All right. So I'm going to give you two, three examples and then leave a question for you to attempt. Right. So the key thing I want you to take from this now is, let's say we have a point here, I will call this A, and we have a point here, I will call it B, right? And if we join these 2 points, right, we have to put a north here and a north here. Now, having done this, we have created parallel lines. These two are now parallel lines. And if I am to put this one as 65 degrees, and then we want bearing of B from A. And then we also want the bearing of A from B. Now, I want you to understand what is happening here. We said we measure bearing starting from north. That's the first thing. And we measure clockwise, right? So, from this now, the bearing of A from B, we go with the bearing of B from A, we go where A is, here. North, we measure clockwise, so the bearing of B from A is right, this end, which we are given as 65 degrees. But I have highlighted that we write the bearing in as three figures. So we have 0, 6, 5 degrees. Okay? This is how we write our bearing. And now we want the bearing of A from B. So we will go where B is and we will measure clockwise from north. Right. So I want you to see this. This is where we apply the parallel lines laws or theorems. Right. If you are to check, this is 65, and I talked about co-interior angles and say that they add up to 180. So this angle and this angle should add up to 180. So 180 minus 65 should give us 5 here, 1 here, and 1. So this is 115 degrees, right? So we want this part now, this one. So what do we do? We say 360 minus 115, and we get 5, 4, 2, right? This is how our bearing of B from A, which is 2, 4, 5. Or you can even say, if this one is parallel to this one, it now means that this part is 65 degrees. And a straight line is 180 degrees, by the way. So 180 plus 65, we get 5 here, 4 here, carry 1, 2, 4, 5, like this one, no problem, right? So that's how we calculate our bearing, right? Let me give you another example before I leave a question for you. we have our P here and our Q here, a point here and a point here. So this becomes our north, and this becomes our north as well. And we have an angle which is 50 degrees here. Right. So we want the bearing of P from Q, and we also want the bearing of Q from P. Right. So what I want you to see here is these two will form parallel lines. Right. And if you want, you can even say if this is 50, this one is also 50. Right. And for the first part, and we can even have this one is what is 180 minus 50 is 130, right? Okay. And this one is also 130, right? 180. Right. So the bearing of P from Q, P from Q, right, will be from Q to P, and we will measure from north, that's the first thing. Clockwise, that's the second. So